What was his name? Like the seniors,
Okay, my friends, if anybody's watching this, I'm glad.
Like and subscribe. People like and subscribe.
I'm gonna post you Mr. Morris YouTube channel on every social media.
Don't do that. It would be so boring for
You're
people.
gonna get so many subscribers.
I don't think so. I'm pretty sure I won't. What?
You should monetize your videos.
Yeah, get some money.
Put those ads.
Well, right before you watch it.
You gotta be kidding me. You're joking.
A little more on the side.
Let's do it, guys.
All right, let's go back to this. Now, so we have diffusion, the spreading out of a gas. Effusion is when you have a gas that's in a container and the container is even sealed, but it's got a small opening in it. So the gas is able to escape out. The best example I can give you of effusion is when you put helium into a rubber balloon. The balloon is beautiful and big and fluffy and it's rising up and you know, you carry it through the door. And the next day, it's on the floor. I know, it's such a sad thing. The rubber it's got holes in it and it's not totally sealed. So that's not a great container for a very small atom like helium. If it were air, it would take much longer for the air to effuse out of there because, well, for two reasons. We're going to find that because of Graham's law, it's going to take longer. But also, the molecules are bigger in the air than they are in helium. So they don't fit through those little openings as well. That would escape even faster. Yeah. Even two hydrogens attached together would it be smaller than helium? No, I take that back. Hydrogen would be a little bit bigger, so it would take hydrogen, even though it's a smaller mass, longer to get through. Yeah, that's interesting. Because of the size of the opening in the helium, that's the main thing. Oh yes, yeah. If you light it on fire, it'll get out much faster. Yeah. Okay, so here's what we're going to do. Graham came up with this relationship. Really, when you see this thing derived, you're like, this guy is like immortalized because of this. But anyway, yes, he is. So assume that now Graham's law is about comparing two different gases, the rate of diffusion of two different gases. So you need to assume that they're at the same temperature. This assumption must be true for Graham's law to exist. You can't compare the motion of one gas at 30 degrees to a different gas at 60 degrees. Graham's law won't do that. They have to be at the same. So if their kinetic energies are equal to each other, and they will be if they're at the same temperature, that means that their expression for kinetic energy would be the same. I'm going to rewrite these two. I should have not written that, but like this. 1/2 m1 v1 squared equals 1/2 m2 v2 squared. I am just kind of distributing that one so that we can keep track of which gas is which. So we have gas 1 and gas 2. Now remember, the m refers to the mass of one gas particle. And the v is the velocity. What Graham did when he came up with this law was he established that, okay, you got two gases at the same temperature. He moved the similar terms to one side and then the other similar terms to the other side. And what I mean by that is like this. First of all, if you take this relationship and multiply both sides by 2, the 1/2s go away. So now we're just down to m1 v1 squared equals m2 v2 squared. Dividing both sides by v1 squared is going to cancel it from that side, but it just moves the v1 over to the right. So it's going to be gone from that side. And then taking the mass, so what Graham did was he put the masses on one side and the velocities on the other. So you're going to divide out the mass from the right side, m2 on the bottom here, and both of those. So m2 is going to be gone from that. So now cleaning this thing up, it looks like this. On the left side, we're just down to m1 over m2. On the right side, we're stuck with v2 squared over v1 squared. This is just manipulating this equation and moving things around. I'm not inventing anything. Okay, now the next thing is to make sense of these terms. The mass of gas 1 over the mass of gas 2, remember the m represents the mass of one particle. The mass of one particle is very inconvenient because particles are so small. And you can't even measure them because they're so small. Is there a proportional thing that we could do with this relationship to make it more measurable? Instead of mass of one particle over the mass of another particle, how about we multiply the top and the bottom by Avogadro's number? What would that do for us? That would be the molar mass then. That's something that we can deal with. So that's what is done here. I'm going to call it, instead of just the mass, molar mass of 1 over the molar mass of 2 equals, and for this side, we're talking about the velocity of particles. The velocity is going to be proportional to the rate of diffusion or effusion. So instead of using the term v, I'm going to call it rate instead. Isn't velocity just a rate anyway? So are we okay if I change the v to the word rate? Because it's the same thing. Okay. Rate of 2 squared over the rate of 1 squared. Now, this is getting us very close to what Graham's law looks like. And I've kind of backed myself into a corner here. Maybe I'll extend the page. Oh, yeah. Okay, so Graham's law, I would be perfectly fine to leave it like this and say, okay, this is Graham's law, we'll use this. But when you look it up in a book or on a website or whatever, it never looks like this. What they wind up doing and what Graham wound up doing is taking the square root of both sides to get rid of the square terms. I like the square terms better than square roots myself, but it's not Moore's law. Right? So we're stuck with it. Now, just so, because we're comparing the rates of diffusion of these two things, I'm going to take these two and turn them around. I'm going to put the rates on the left and the molar masses on the right, but not change anything else about them. Taking the square root of both sides, the rates are going to lose their squared terms. Again, I'm taking the square root of both sides. So the molar masses then will be under a square root. This thing right here is what we know and love as Graham's law. The most common mistake people make using Graham's law is they use, if they have rate 2 on the top over here, they want to put the molar mass of 2 on the top over there. What I always remember about Graham's law is whichever gas goes on the top in the numerator on one side, the other gas has to go in the numerator on the other side. You see that? On the left, gas 2 is on top. On the right, gas 1 is on top. That's not a mistake. That's correct. So, maybe I hit it with my elbow. So anyway, just do make sure that you know what, and it doesn't matter. You can put 1 over 2 on this side, but just make sure if that you do that, you put 2 over 1 on that side. So Graham's law will still work out the same. I have an exercise for you. I want you to try this problem. It's a Graham's law problem. We're talking about diffusion of 2 different gases through a meter-long tube. Gases spreading out through this tube. What would be the molar mass of one of the gases?
The rate and velocity is the same, right?
What?
The rate.
Yeah.
Is the rate's not squared, right?
No, it was being squared, but now we just leave a rate to the first over rate to the first is the square root of the molar mass. Yeah, no, don't ask me what methane is. You got to remember that. In memory? What did you just say?
I need to figure out the table because I don't have the things.
Oh.
What's the molar mass of methane?
16,
I used methane on purpose because it's got a molar mass that's a perfect square. Yeah?
Are you trying to be a teenager now?
What is it? 16 don't do
Use
it.
lingo.
Just put 16.
Wait, why does it matter?
I have teenage kids at home, and they're sure to let me know when I shouldn't be acting like a teenager. Dad, just stop. Thank you. I'll tell them that.
Mr. Moore, was this one of those questions where you don't want us to use a calculator?
You would want to use a calculator for this, yeah. If I didn't let you use a calculator for this, the numbers would be nicer. Use a calculator.
Alright.
Did you do it already?
Yeah. So on a test, you get a calculator with this kind of problem.
Yes. Yeah. I could have made the numbers nicer, which would have given us a, I mean, you can estimate an answer for this. I think I'll let you use a calculator. And by the way, this is a dirty, rotten, sneaky problem. I hope that you've thought about it carefully, if you're done. Because I'm giving you the time of each of these. Time is not the same thing as rate, is it? Well, it looks like you guys are on to me. That's good. That's good. Our distance of this tube is 1 meter. So let's see. Is it okay if I go ahead and start putting the solution up here? Okay. It would be
At least you didn't say lit.
I don't say what?
Just said lit once.
Lit?
Lit. L-I-T.
Like getting lit?
Like this is.
I wouldn't say
We
that.
were all like, oh my god. I was thinking about. I was like,
Mr. Moore, you don't get lit, you just lit. You are.
I hope you don't get lit.
I hope I didn't catch on fire too.
Terrible.
Daniel, let's keep it at that. Okay. Whichever gas I put on top on this side, I'm going to put the other gas on top on the other side. So I have 1 meter over 50 seconds. That's my rate of methane. So if methane is on top on the left, I better put the molar mass of the unknown gas on top on the other side. And that is what I don't know. I'll put MMU for molar mass of unknown. And then the molar mass of methane is 16. And solve. It's not bad. Watch out for problems like this where you're given the time, though, not the rate. I can remember there is a question on the practice test on this chapter, at least one question, where it's like this. You're given the time of diffusion or effusion, not the rate. So just watch out. If you're given the time, you know the time is inversely related to the rate. So you wind up getting the reciprocal relationship on the one side. Are you with me? So watch out. Okay, so just solved. You're going to get a molar mass of 92, I think, something like that. Now, with this is kind of weird because it says a meter-long tube. I just used the words. I think that means that we're stuck with 1 sig fig because I didn't give you any other. So you could just call it 90 and it's good. I think 92 or